Now that we have a basic understanding of bits, binary, and 2's complement from the past video, we can now move on to talking about bit manipulation. Bit manipulation. It refers to the art and science of algorithmically altering the binary bits that represent data on a computer. Since computers fundamentally operate on bits, binary digits, being able to effectively manipulate these bits can be pretty useful, as I'm sure you'd imagine. All forms of data that reside on a computer, regardless of their type or abstraction level, are ultimately stored as a series of bits. This includes integers, floating point numbers, characters, and even more complex structures like strings and arrays, since at the end of the day, these more complex structures are just essentially contiguous blocks of memory, each addressable and ultimately represented in binary bits. Bit manipulation utilizes bitwise operations, which usually have their own mnemonics for the ISA, instruction set architecture, of most computers. They are also accessible in most, if not nearly every modern-day programming language in existence through the use of bitwise operators. Bitwise operators are, generally speaking, much faster than arithmetic operators, and allow for lower-level control over values. They also leave a smaller memory footprint depending on what you're doing, meaning that if you have a limited amount of memory, bitwise operators could be useful. One example of this is packing a lot of flags within a single integer to represent lots of different information all at once. Arithmetic operators aren't very useful in this scenario, since the goal is to read and manipulate individual bits as opposed to decimal numbers. Really, this only matters if you're doing something intense like game development or bare metal programming, though I'm not entirely sure or aware of every context in which bit manipulation is actually used. The use of bit manipulation can also be found in graphics encryption algorithms, data compression algorithms, low-level device control, like with microcontrollers, and in the optimization of algorithms in general. So now we can go over each and every single one of the bitwise operators. The first bitwise operator that we'll go over is binary AND. This operation compares 2 bits and returns 1 only if both bits are 1. Otherwise, it returns 0. For example, 1 and 1 results in 1, but 1 and 0 or 0 and 1 results in 0. Another way to think about AND is how it's used in Boolean algebra. Boolean algebra, originally created by George Boole, uses binary values, often represented as on-off or true-false values, to conduct logical operations. And really, it's the foundation behind logic gates and digital logic in general. If you've ever written a Boolean expression, you know that the AND operator returns true only if both operands are true. And this is exactly how the AND operation works in the context of bit manipulation. In this case, 0 is false and 1 is true. The next operator is binary OR. This operation compares 2 bits and returns 1 if either of the bits are 1. It only returns 0 when both bits are 0. For instance, 1 or 0 or 0 or 1 results in 1, and 0 or 0 results in 0. Once again, we can think about OR in the way it's used within Boolean algebra. If we write a Boolean expression with an OR operator, it returns false only if both operands are false, otherwise it returns true. Again, 0 is false and 1 is true in this context. Next is the XOR operator. This operation compares 2 bits and returns 1 if the bits are different, and 0 if they are the same. For example, 1 XOR 0 or 0 XOR 1 results in 1, but 0 XOR 0 or 1 XOR 1 results in 0. Then there is the negation operator or the NOT operator. Also, you could think about this as 1's complement, and this operation inverts all the bits of its operand. If the bit is 1, it becomes 0, and if it's 0, it becomes 1. For example, NOT of 1 results in all bits of 1 being inverted, becoming either -2 or 254, depending on if it's assigned integer or not. It is worth noting that in Boolean algebra, the NOT operator works identically, as in it produces the opposite logical value of the expression, and we can think of the NOT operator in the same way within the context of bit manipulation. Then there is binary left shift. This operation shifts the bits of the first operand to the left by the number of positions specified by the second operand. It is equivalent to multiplying the first operand by 2 raised to the power of the second operand. Good example of this is 1 left shift 2, which results in 4. Then there is binary right shift, and this operation does the exact opposite. This operation shifts the bits of the first operand to the right by the number of positions specified by the second operand. It is equivalent to dividing the first operand by 2 raised to the power of the second operand. And another good example for this is just 4 right shift 2, which results in 1, which reverses what we did in the last segment. This next segment of the video is going to be dedicated to different techniques using the bitwise operators. The first technique is going to be zeroing registers. In assembly, the ZOR mnemonic is used for zeroing registers, since any 2 bits that are the same in each of the operands will result in a 0. This means any number that is ZORed by itself becomes 0, making it possible to zero a value or register if the first and second operand are the same. So here I have an example of this being used. This is Linux 32-bit assembly, Intel syntax, x86 of course, and it's very straightforward. Even if you don't know how to read assembly, you should be able to reason about this. We're simply moving the value 1 into the EAX register for the syscall number, moving the value 69 into EBX for the exit code, and then we are ZORing EBX by itself to zero out the register completely, and then we perform a syscall to exit with the number in EBX, which is now 0 after we zeroed it out. So to make things a little bit clearer, I've decided to use a regular programming language, decided to use C. Same exact thing is happening here, except instead of a register, we're using a variable. We define a variable n with the value 69, and then we set it equal to n ZOR n, and this completely zeroes out the value, and then we return with that at the end to exit with a code of 0. It's the exact same as the previous code, just in a easier to read programming language. The next technique is kind of fundamental. Like, without this, you cannot do the majority of bit manipulation, and that is bit masking. Bit masking is extremely crucial. Bit masking is a technique used to manipulate specific bits within a binary number by using a mask. And the mask is just a binary number where certain bits are set to 1 to select or affect those specific bits, or 0 to ignore or leave certain bits alone. Bit masking is used for operations like setting, clearing, toggling, or checking the value of particular bits within a number. And every single thing that I just said, we will at some point cover in this video. It's a fundamental concept in low-level programming and is used across various applications, including but not limited to hardware control, data compression, encryption, and far more. Bit masks can also be used to combine or isolate multiple bits from a number simultaneously, which is useful in applications where multiple flags or settings are stored within a single integer. You can create a mask in a lot of different ways, but the simplest way to do it is simply to left shift 1 by n being the nth bit or some operand. Here I have another example, this time with some Go code, that produces a binary value with 1 left shifted to the value of n. This means you can make the nth bit a value of 1, targeting it for various reasons. Do note that this is 0 indexed since we're left shifting by the value of n. Shifting once would give us a value of 2, or 0010 in binary. And what about targeting multiple bits? Well, we can do that too. In this code, we now target the second and the fourth bit in the number by using the OR operator on the values 10 or 2 to the power of 1 and 1000 or 2 to the power of 3. You've effectively set 2 bits to 1. The reason for this is quite simple. An OR operation will compare 2 bits and evaluate to 1 if any operand contains a 1, which makes it especially useful for combining bits and creating masks that target multiple bits in the way we've done here. You can also use the 0b prefix in a lot of different languages to write explicit binary values directly, which you can also use for creating bit masks as well. The first technique we'll go over regarding masks and using masks is reading bits. To check the value of specific bits, you can use the bitwise AND operator with a mask where the targeted bits are 1. If x and 1 left shift n is non-zero, then the nth bit is set. The reason for this is simple. If the targeted bit is 1, then the AND operation will result in 1, and the number produced will be larger than 0. Otherwise, the AND operation will cause all bits to be 0. Including the bit that's targeted, since it's already 0. This results in you zeroing out the number, and you'll find out if the targeted bit is a 1 or a 0. The code above illustrates this, as it's a simple program that creates a mask using the value 2 to check the third bit in the number 5. This results in an output of 1, since 5 is equal to 2 to the power of 2 plus 1, which means the third bit is going to be 1. This allows you to find the value of any bit in any number at any position. Next, we'll go over clearing bits. To clear specific bits or set them to 0, use a bitwise AND operator with a mask where the bits to be cleared are 0. This will cause all other bits to be unaffected, since if the bits are 0, they remain 0, and if they are 1, then they remain 1. However, the targeted bit will change to 0, since the result of the AND operator is 0 if any of the operands are 0. Creating a mask like this is easy. You just take a regular mask that uses ones to target bits, and you perform a NOT operation on it, flipping all of the bits, and now 0 will target all bits for clearing. The above code illustrates this once again. I used C++ because passing by reference makes things easier here, allowing us to mutate n because we are passing in a reference to it, and the negation operator in Go is kind of weird, so I wanted to keep things a little simpler. Next is clearing a range of bits, which is really the same as what we did before. The only difference between clearing a single bit and a range of bits is the bit mask itself. If more than one bit in the mask is 0, then every bit with a 0 value will be cleared after doing an AND operation, while all the bits in the mask that are 1 will remain unaffected. Next is replacing bits. To replace a segment of bits in a number, you can first clear the segment of bits, then perform a bitwise OR operation with the bits you want replaced. And I think this is pretty easy to understand, because when all bits are 0, performing an OR operation with any bit will fill in the bits exactly, since the OR operation results in 1 if either operand is a 1, which means a 1 and a 0 result in a 1, and a 0 and a 0 result in 0, which means all bits remain unchanged after being OR operated on. The next technique is setting bits, and to set specific bits to 1, which is what a set bit is, a 1 bit, you can use the bitwise operator or with a mask where the bits to be set are 1. This makes sense because regardless of whether or not the bit is set, the result is always 1, which means using the OR operation will ensure a bit is set to 1. This code just passes in a reference of n to a set bit function, creates a mask based on whatever is passed in as I, then performs an OR operation to set that specific bit in the mask to 1. And now we can move on to toggling bits. To toggle specific bits, you can use the bitwise XOR operator with a mask where the bits to be toggled are 1. Using a XOR works because XOR always produces a 0 if both bits are the same. This means that when the mask is all 1s, any 0 bit in the original number will be converted to 1. And if it's a 1, it'll be converted to 0. Essentially, it gives you the opposite of whatever bit is in the number. Now we can move on to counting the number of set bits in a number. You can count the number of bits set in a number by iterating through each bit and adding them all together. If the bit is a 0, it won't increase the value of the count, and if it's a 1, it will increment the count. You iterate for as long as the number is more than 0, because that means that there are more bits in the number to be iterated over. We can see this being achieved in the first block of code. N and 1 will always return the last bit in a number, so once you have the last bit, you can add it to the count to keep track of the amount. Then do right shift to drop off the last bit, so you can continue on with the next bit until you've iterated over every bit and right shifted to the number 0. That is the naive approach, but there is a much faster and more optimal solution that works slightly differently. It's known as the Brian-Kernighan's algorithm, I believe I pronounced that correctly. It keeps track of the count the same way, but performs a bitwise operation that removes the last set bit from the number by setting n equal to itself, but doing a AND operation on n-1. Then increments the count each time this is done. This means for every bit that exists in the count, it's incremented, and this will only iterate for as many set bits that exist, making it faster than the first solution. The last technique in this video will be how to convert decimal numbers to their binary representation, but in decimal format. The approach we'll take in doing this will actually take us all the way back to the beginning of this video. Well, actually, the Art of Bits video. Remember how I said that every digit is just an exponent of its base, and how the further left you go, the higher the exponential value? Well, we can actually use this information to represent binary numbers in decimal format by essentially multiplying by our base. That is what the convert to binary function does. The function starts by initializing a value of 0 in a variable bin, and it will add to this variable for the duration of its implementation. First, it loops for as long as n is more than 0, which means that there are still bits left in the number. And just like our counting bits function, the first implementation, we will get the last bit in the number by using n and 1. At the end of each iteration, we will right shift n to drop off the last bit. This is actually very similar to the count bits function, but with some differences. The p variable of 1 is used to keep track of the placement of the digit, where it's multiplied by 10 each iteration to move left once. Each iteration, the value of the last bit is multiplied by the current exponential value of 10. P for its placement, then gets added to the value of bin, and when we have iterated through the bits, we get a number that looks like the binary representation but in decimal format by multiplying by the base, more specifically base 10. That about covers the basics of bit manipulation. Hopefully you learned something, and once you understand how these operations work, you can get pretty creative and do some pretty interesting things. Anyways, I appreciate your attention and thanks for watching.